In lecture, you were posed with the question of why is the minimum velocity curve also the shortest distance curve? In this segment, we'll discuss the answer to this question. Recall that to find the minimum velocity curve, we solved for the trajectory x star of t that minimizes the integral of the cost function x dot squared. We were able to use the Euler-Lagrange equation to find that the general form of the solution is x of t equals c1 times t plus c0. Now, let's find the minimum distance trajectory. Given 2 points, A and B, we want to find the trajectory that is the shortest in total length. We can find the length of a trajectory between A and B by integrating infinitesimal segments ds along the curve. Each infinitesimal segment ds has a corresponding change in dt and a change in dx. We can find the length of the segment ds using the distance function. We can rewrite this function by factoring out a factor of dt from under the square root. In the second step, we've used the fact that by definition, x dot is equal to dx dt. To find the total length of the curve, we want to integrate ds along the entire curve. Substituting in the expression for ds we just found, we find that the length of the curve can be found by taking the integral from 0 to t of the square root of 1 plus x dot squared dt. We can now mathematically represent the problem of finding the minimum distance trajectory in the familiar form, finding the function x star of t that minimizes the integral of a cost function with respect to t. In this case, the cost function L is the square root of 1 plus x dot squared. Again, the necessary condition for the optimal trajectory is given by the Euler-Lagrange equation. To find this condition, we need to evaluate the Euler-Lagrange equation for our cost function. We can start by evaluating each term in the equation. The partial derivative of L with respect to x is 0. This is because x does not appear in the cost function L. The partial derivative of L with respect to x dot is x dot over the square root of 1 plus x dot squared. Note that this is the partial derivative of L with respect to x dot. That is, we are not taking any derivatives with respect to time yet. To use the Euler-Lagrange equation, we need to find the time derivative of partial L partial x dot. However, it turns out that we don't need to explicitly calculate this. Substituting the terms we found into the Euler-Lagrange equation, we get the following expression for the necessary condition for the minimum distance trajectory. We can directly integrate this expression with respect to time to get an expression for the velocity of the trajectory. Here, k is an arbitrary constant. We can solve this equation for x dot. We see that x dot is a function of only the constant k. Therefore, x dot is a constant and does not vary with time. We can relabel this constant as c1. We can integrate the expression x dot equals c1 to get the position function of the minimum distance trajectory. This gives us the expression x of t equals c1 times t plus c0, where c1 and c0 are arbitrary constants. We see that this is the equation for the minimum velocity curve. Thus, given the same set of boundary conditions, the minimum velocity trajectory will be the same as the minimum distance trajectory.